we have finished calculating curve length, and now we have calculated curvature surface. For that, we have taken example of a sphere, and we calculated the surface of a sphere through a method that we have proposed. So we have proposed a method to calculate the surface of a sphere. But we will proceed in the example of a sphere itself, and then we will see that what can be other way we can calculate the surface of a sphere. That is a small kind of entity, that a small kind of surface of a sphere through other way. So kind of small progress that we will do with the other example, but bigger leap we have done in a way that we calculated through Cartesian coordinate. So the idea of this kind of this session is, can we calculate the surface area or line curve length? Can we calculate curve length and surface area of curve length and surface area 2D and 3D with Cartesian coordinate? We successfully finished both of them. Now, for the curve length, we have a position vector, and then dp by dx. We find if we have dp by dx, then x component square plus y component square root is the dl by dx, d length by dx. And if that is the case, okay, if that is the case, d length by dx. Now, if I integrate, then I get the curve length. Curve length through Cartesian coordinate. That is the concept. Curve length through Cartesian coordinate. Now, if I have position vector, like we take example of a circle, and position vector is xi plus yj, xi plus yj, where x square plus y square equal to 1 being radius, then xi plus square root of 1 minus x square j. If that is the case, then dp by dx is I minus xy square root of 1 minus x square j. If that is the case, then d length by dx, okay, if this is the velocity vector is I minus xy square root of 1 minus x square j. If this is the velocity vector, the length algebraic equation is x square plus y square of a vector. Then 1 square plus x square by square 1 minus x square root. That will come as 1 by square root of 1 minus x square. Now I have to integrate 1 by square root of 1 minus x square from left to right along the x-axis, and I get the net length. We describe in the detail that what actually we are doing to calculate, what actually we are doing. Okay, so what actually we are doing, calculating the length. So if I have a circle, and circle is centered at origin, then from origin, if I draw a line to all points on the circle, then this is a kind of radial vector. This is something that is radial vector or position vector. If this is x comma y, this is x comma y, this is x comma y, and this is origin, then from origin, all point if I start touching, then P is shifting. One point on the circle x comma y is a point P. If point P is there, then this is vector P. Now, if x comma y I keep shifting, this vector starts shifting. Okay, when it starts shifting, then P is moving. If P is moving, then per unit shift in X brings how much shift in the P, dP by dx. If dP by dx, then dP by dx we saw it's a velocity vector, and if this is position vector radial to the kind of curve of a circle, then velocity vector is tangent. So if I keep moving x comma y, then velocity vector would move like this. If it moves like this, then if I calculate the magnitude of the velocity vector, it is the length. Length in algebraic equation. If I have length in algebraic equation, then dp by dx, dp by dx is velocity vector. Now if I have length of velocity vector, okay, if I have length of velocity vector, or I generally say dl by dx, so if I have velocity vector magnitude, then now if I integrate this magnitude of the velocity vector, then it becomes the net length. If I have magnitude, if I have direction of the velocity vector, and if I integrate that, it comes back to position vector. Velocity vector, position vector. Position vector differentiation becomes velocity vector. Velocity vector integration becomes position vector. Velocity vector's magnitude integration becomes length of the position vector. But can we find directly as far as algebra is concerned? Now suppose this is origin, and this is x comma y. So if radius is 1, then this is 1 comma 0. I mean 0 comma 1. So if this is x-axis and this is y-axis, if this is center, then this is 0 comma 1. Now if I have a position vector here, x comma y, then what is distance between these two vectors? If I consider this is the beginning of the curve, this is beginning of a curve, this is the negative length and this is the positive length. If this is beginning of the curve, then at any x comma y, what is the length? That is the length. Why I went for kind of calculus? So the vector is 0 comma means j. The vector here is j because x is 0, j, and here xy is xi plus the square root of 1 minus x square j. Now from here to here, if I draw a vector, then that becomes xi plus the square root of 1 minus x square minus 1 j. Now what is the length of this vector? That is x square, okay, x square plus now this one whole square. That is square root of 1 minus x square plus 1 minus 1. This position vector here is xi plus a square root of 1 minus x square j. Okay, xi plus a square root of 1 minus x square j. Now this position is 0 I plus j, 0 comma 1. If I subtract this, this gives me this vector, that is xi plus square root of 1 minus x square minus 1 j. Magnitude is x square plus square root of 1 minus x square plus 1 whole square and then square root. So x square plus, now in braces, square root of 1 minus x square plus 1, brace close, square and then whole square root. Now keep changing x and you are getting the length. The way, if I have velocity vector, if we have dp by dx, magnitude of the velocity vector is length. Length is algebraic equation. Now if I integrate length, then I get length of the velocity vector. If I integrate it, then I get length of the position vector. That is also in function of x. This is also in function of x. Both are same. Then why we went for calculus those kind of things? This is not same. That is the calculus algebra. Algebra as calculus and algebra altogether separately. Like I have numerical mathematics 1, 2, 3, 4, 5, 6. So if I want to calculate the rate of change, then rate of change, like someone is walking at 5 kilometer per hour, and at the end of 3 hours how much he is get. So rate of change is 5 kilometer per hour. At the end of 3 hours, how much distance he travel, rate of change into the independent numerical. So everything in numerical here. 5 into 3, so 15 kilometer he walked. If collection is 15 kilometer in 3 hours, then what is rate of change? 15 by 3, 5 kilometer per hour is the rate of change. This is numerical mathematics. But then what is calculus? Calculus is when we replace these numbers to algebraic equation. When it varies, here everything is constant, but it start varying for each value in x, where x is infinite value, set of value. For each value of x, if y starts changing, then y we place in terms of independent component function over x. If I have algebraic equation, then I want rate of change, then I have to use calculus differentiation. If I have rate of change and I want net collection, then I have integration. Everything would result in algebraic equation. Keep changing value of x, you get the net collection or you get the net rate of change. Here, if I have a position vector here and I have a position vector here, and this position vector keep changing, and if I calculate the magnitude, that is the length, that is not the length, that is the length between this point and this point, that is like this, that is like this. This is what we don't want. We want length of the curve. So if I want length of the curve, then I want a algebraic equation that will keep changing along the curve. That is the velocity vector. If I have position vector that keep changing along the curve, then velocity vector is exactly that is tangential and keep changing along the curve. So length along the velocity vector is the length that whatever length we are calculating, rate of change in that length is the velocity vector's magnitude. If I have position vector and rate of change in the position vector is velocity vector, then if I have a length vector, some imaginary length vector, then rate of change in length vector is magnitude of the velocity vector. If I have magnitude of the velocity vector, then if I integrate, I get the net length. So the length of the velocity vector should be variable because velocity vector is touching every point as tangent. So then if I integrate this velocity vector magnitude, then it would result in the actual length of the curve. That is the science. So if I have position vector, then its position vector, then its differentiation is velocity vector. If I have a length vector, some hypothetical, then its differentiation is the length, is the length. That length is nothing but magnitude of the velocity vector. Integrating it, I get the length. That is the concept. So we have calculated the length of the circle through Cartesian coordinate. Now we will calculate length. Now then we calculated surface area of a sphere through Cartesian coordinate. So in that sense, we saw that surface area is nothing but if I have a sphere, if I have a sphere, okay, if I have a if I have a sphere, then a sphere there are two independent components. If I have a circle, then there is one independent component, that is x-axis. If I have a sphere, then two independent components, x-axis, y-axis. Now each point x comma y, for each x comma y point on the xy plane, I have a z value, that is fxy, that is dependent component. If I connect all the z value, I get a sphere surface. if I have only one independent component, x-axis, and if I have fx function over x that is vertical, then if I connect all the vertical point, it will be a line. But if I have xy plane as independent component plane, and for each xy plane, if I get the z value or fxy, if I connect all the z value, I get a surface, line surface, 2D, 3D. So if I have a sphere which equation is fxy equal to x square plus y square, okay, fxy equal to radius square minus x square minus y square square root. Or in other way, I can say x square plus y square plus z square equal to radius square. That is the equation of a sphere. So fxy equal to radius square minus x square minus y square square root. In 2D, in line equation, okay, fx equal to radius square minus x square square root. If I take the radius 1, then z equal to square root of 1 minus x square minus y square. Now, we saw that now if I have a z, if I have fxy, then in xz plane, what is dz by dx? So if I have a position vector, if I take up any point P on the sphere, okay, so if I have a sphere, okay, so if I have a sphere, okay, so if if I have a kind of if I have a sphere, then sphere is centered at the origin. Now I take any point P. What is the coordinate of P? That is x comma y comma z, or x comma y comma fxy. If that is the case, then what is dp by dx? dp by dy? What is differentiation that is seen in the dp? What is rate of change in P? So there are two independent components. So rate of change in P along x-axis, rate of change in P along y-axis, dp by dx and dp by dy. If I calculate these two dp, then I get velocity vector along x-axis, I get velocity vector along y-axis, okay, at any point P. So at point P, I have a velocity vector along x-axis, I have velocity vector along y-axis. Okay, P, the surface is curved, it's not flat, it's not parallel to xy plane, but the velocity vector is parallel to x-axis and y-axis. dp by dx, dp by dy, they are algebraic equations, they are not that simple. So if I keep changing P, then velocity vector will also keep changing like this along x-axis, it will keep changing along y-axis like this. Okay, whatever net come, that is the two. If I do cross product of these two velocity vector, cross product, then I have a velocity area. Velocity area, velocity area, not actual area what we are trying to get. If I have velocity area, the way earlier in the curve length, I had a velocity length, then I have a velocity area. If I do dp by dx cross dp by dy cross. Why cross? Because if I have a length, and if I have a width and length of any rectangle or any parallelogram, okay, if I have width and length of any rectangle, then width into length is the area. But what about if I have width as one vector and length as another vector? What is the area? That is cross product. So even if it is parallelogram or whatever, cross product will give the area. So if two lines are in same direction, so vector is better line. If line is good, then vector is better because it has direction now. So I can say I have a width, I have a length, then I don't know there is a 90-degree or not in between. That should be there to multiply to get the area. But what about they have some direction, not necessarily 90 degree. Then I have a length, width vector and length vector. Now instead of now if I multiply, then I get the area. There is no multiplication direct. So if I do cross, then I get the area in between. So if they form parallelogram also, angle is not 90 degree, but still I get the area. That is the concept of the vector. Now dp by dx I know, dp by dy I know, these two vector I know. Okay, but anyway, here dp by dx and dp by dy, these vectors should be perpendicular because they are derived in a orthogonal axis. But whatever it is, if I want area through vectors, then I have to use cross product. So if this is the dp by dx, this is dp by dy, if this is the area, then the cross product result in a vector. The direction of vector will be perpendicular to the xy plane. That is the concept. Now dp by dx and dp by dy, if I cross it, then I get kind of a sense of area vector. Sense of a area vector. Now let's calculate the magnitude of the area. Or I can say area velocity. If dp by dx is velocity vector along x-axis and dp by dy is velocity vector along y-axis, then dp by dx cross product dp by dy is area velocity vector, whatever. Now, if I want the surface area, then I have surface area of area velocity vector, not the actual what we want. Then I have to calculate the magnitude. Now let's see that if I have a point x, p point and xi plus yj plus fxyk, then what is dp by dx? Then it is I plus fx, fxy, dfx by dx, I call it fx, f, and in subscript, then I place as x, fx. So I plus fxj, and dp by dy is j plus fyk. If I do cross product of these two, then they would result in j minus jfx minus ify plus k. Anyone can do the cross product. And now if I want the magnitude of velocity area, that will be the magnitude velocity area is dp by dx cross product of dp by dy, that is minus fxj minus fyi or minus fyi minus fxj plus k. Now this is velocity area vector. Now if I want this amplitude, that will be fx square plus fy square plus 1 square root. Now this is the velocity area vector's magnitude. Okay. Now this magnitude, if I integrate back, then I'll get the surface area, the way I got the length. So it will come as 1 square plus fx square plus fy square, a square root, and then I integrate, then dx and dy I'll put, and then limit of minus x to minus x, x left side limit, right side limit, and y both limit I'll put, then I get the surface area. How simple it is. When I am doing derivation along x-axis, doing derivation along y-axis, but surface area is completely curved, then if I multiply these two vectors, then I'll get the flat surface, not the curve area. This is wrong, right? This is right. If this is right in curve length, then it is right here also, because the velocity vector along x-axis and y-axis, they are in formulation of algebraic equations. If you keep changing velocity vector, they will change like a curve. They will not change like a flat surface. That is the catch here. In circle, if I had a circular, okay, if I had a circular, then if I have a velocity vector, then that is tangential. Okay, but velocity vector is kind of tangential, but it has both component, I component and j component. So if I do dp by dx, it has all three component, I component, j component, and k component. Okay, now I think it is more clear. So dp by dx is a vector which may not be kind of parallel to the x-axis. dp by dy is a vector which may not be parallel to the y-axis because it has I, j, and k components. I think it is more understandable. But idea is, after all, we are differentiating along x-axis. that is, and then we are differentiating along y-axis. Actually, we are differentiating p on xy plane. So dp by dA, this is with what we are getting. dp by dA is a vector that has x component, y component and z component, and that vector would be in some scenario. If I get the magnitude of dp by dA, then that is the area, area of the dp by dA. If I integrate it back, then I get the surface area. Okay, so I would repeat it. So if I have a point P here, if I have a point P here, and P is nothing but a vector I, j and k, then that is xi, yj and fxy, k. Okay, if I differentiate along x-axis and y-axis dp by dx, dp by dy, then it becomes I plus fx k and j plus fx plus fy k, dp by dx and dp by dy. Now dp by dx and dp by dy, these are two velocity vectors along x-axis and y-axis. But the actual vector is, if I keep changing, now it is I plus fxy, I plus fx k. Fx is nothing but dfxy by dx. Now here, like in a sphere, fxy is 1 minus x square minus y square square root. So dfx by dx is minus x by square root of 1 minus x square minus y square. Dfx by dy is minus y square root of 1 minus x square minus y square. Now if I see dp by dx vector, that is I minus xy square root of 1 minus x square minus y square j, and dp by dy is j minus y divided by square root of 1 minus x square minus y square k, then these two vectors are not along the x-axis or y-axis. Their differentiation is along x-axis and y-axis. But these vectors are not along x-axis and y-axis. These are velocity vectors. So if I take dp by dx, then it will keep changing along the x-axis. Along the x-axis, it will keep changing like a tangent. dp by dy along y-axis, it will keep changing like a tangent. So dp by dx cross dp by dy cross product, if I do, then I try to get, if there is a vector that changes, if there is a vector that changes like this along x-axis, if there is a vector that changes like this along y-axis, then how this vector would change along the xy plane, dp by dx cross dp by dy. No one stops anyone to imagine it. Along x-axis, I showed that it is a tangent change. Along y-axis, it is a tangent change. If it is along xy plane, then there is a surface that is tangent and that is changing. Makes sense, right? This is the subtangential surface now. Now this tangential surface is changing now, because dp by dx cross dp by dy is dp by dA. A is xy plane. Now along xy, if I make change in xy plane, how much dp vector will change? So dp by dx is a velocity vector line. dp by dy is a velocity vector line, but dp by dx cross dp by dy, this explanation is not available anywhere else. So dp by dA is a tangential surface now. So now tangential surface is going like, passing like this. Now if you remember 2D, then a I had a velocity, I had a circle instead of a sphere. Okay, so instead of a sphere, I had a circle. So velocity vector was changing like this. Now, instead of a circle, I have a sphere. Now, velocity vector, one velocity vector is along x direction, one velocity vector is along y direction. If I do cross product, then there is a velocity surface vector that would now keep changing at any p. If this is the p, then their velocity surface is like this. It keeps changing. How it is changing depends upon the algebraic equation. So that is dp by dA. dp by dA is minus fyi minus fxj plus k. That is the vector. Now minus fx minus fy minus fy minus fy is minus minus plus y by square root of 1 minus x square minus y square I plus x by square root of 1 minus x square minus y square j plus k. This is the algebraic vector. This is not normal vector. This is algebraic vector of a surface. So this is the surface vector and it would keep changing for every point. So for any certain point x comma y, if there is a point called x0 comma y0, there is one point. Substitute x0 y0 here. So that would become y0 divided by a square root of 1 minus x0 square minus y0 square I plus x0 divided by square root of 1 minus x0 square minus y0 square root j plus k. Now keep changing x, you will get dp by dA, the tangential surface vector keep changing. If this is the equation of tangential surface vector, then what is the amount of the magnitude of tangential surface? That is the magnitude of this vector. That is velocity area. That is not the area what we want. So from velocity area, if I want the actual area, surface area, I have to integrate it back. So velocity vector area as a magnitude would become fx square plus fy square plus 1 square root. Okay. Now that is the velocity area surface magnitude. Now integrate it along the x-axis and y-axis to I'm sorry. If this is the velocity area, that is velocity area, the amplitude is fx square plus fy square, where fx is dfx by dx, fy is dfxy by dy, fx square plus fy square plus 1 square root. If it is the velocity surface magnitude, then if I integrate it with xy plane, not x-axis and y-axis. So that is the mistake people generally do. If it is 2D, then there is one independent component, that is, these are matter of research. If you want bigger thing, then your brain should be wider. You cannot break things and try to understand. Breaking any item into that's why I don't like breaking anything in delta x and then I have talked it in bigger way. So if we want to understand anything, then I have to understand as a whole, not breaking into separate part and understanding separate part and then combining all together. This is not the concept. This is not Indian concept, at least. Anyway, now if I have one independent component, then I would think everything through a x-axis. But if I have two independent components, x and y, then I have to think everything with the xy plane. Now forget x-axis, forget y-axis. Now there is only one independent component, that is xy plane. Think from the xy plane perspective. So if I have a point P here, then what is dp by dA? What is dp by dxy plane? If I get that, then that is the tangential surface vector. In 2D, I had a tangential velocity vector, that was tangential vector. Now I have a velocity vector, but that is a tangential surface. dp by dA, dp by dxy plane. Earlier we had dp by dx, that is one independent component. Now we have dp by dxy plane. If I do dp by dxy plane, that is again a velocity vector, but velocity vector represents a surface, that is tangential surface. If I have a tangential surface, then I get the magnitude of the tangential surface at any point. That magnitude, if I integrate it back with the dA, then I get the actual surface area. This is what we saw. Now we took example of a sphere, then the magnitude of velocity vector, that is area, is 1 square plus fx square plus fy square root. Okay, if that is the case, then for a sphere it would result in 1 plus x square by y, 1 minus x square minus y square plus y square by 1 minus x square plus minus y square whole square root. It would result in 1 by 1 minus, I have taken radius as 1 by 1 minus x square minus y square whole square root, means 1 by square root of 1 minus x square minus y square. Now dx dy, or I can say xy plane. Now dx and dy, now integrate x from minus 1 to 1 and y minus 1 to 1, then top hemisphere surface area we will get. Now let's go back to this is what we have discussed. So let's go back to the equation of a sphere. Then it is x square plus y square plus z square equal to 1. If I consider x as cos theta and y as sine theta, then it does not satisfy. Then x as sine phi cos theta, y as sine phi sine theta, and z as cos phi, then it works. Now if I substitute this, then dx becomes sine phi minus sine theta. X is sine phi cos theta, then dx is minus sine phi sine theta. And here down the line it becomes 1 by sine phi. 1 by, okay, 1 minus 1 by square root of 1 minus x square minus y square. So 1 minus x square by y square, then it becomes net, it becomes 1 minus sine square phi square root. It becomes 1 by cos phi. Now dx, x is sine phi cos theta, I am sorry, I will differentiate it with the phi, keeping theta as constant. I differentiated with theta. So x equal to sine phi cos theta, differentiate with the phi. Then it becomes cos phi cos theta. Now here 1 by cos theta, cos phi would go away. Cos theta d phi, that is phi cos theta. Now sine phi cos theta equal to x, then theta equal to theta cos phi, sine phi cos theta equal to x, then phi cos theta is sine inverse of x. I said someone has to prove this, where cos theta is constant. If cos theta is constant, sine phi cos theta equal to x, then phi cos theta is sine inverse of x. If that is true, then this integration came to sine inverse of x. Minus 1 to 1 will come as pi. Now I have to integrate pi dy minus 1 to 1. That result in 2 pi. Or if I use radius as r instead of 1, then it will be 2 pi r square. Then north hemisphere and up hemisphere and south hemisphere, top and bottom hemisphere, if I add, it becomes 4 pi r square. This is our kind of analogy and our proof. There are many proofs that is available for this equation. The one proof that is worth, we will take other examples. So one example that I believe that is worth mentioning here is, now what we have integration. I have double integration, and then I have 1 by square root of 1 minus x square minus y square dx dy or dA. Now If I now what I am seeing here is that and y, x and y are two independent components. They lie in a plane. If they lie in a plane and we are following Cartesian coordinate, instead of Cartesian coordinate, I can use simple polar coordinate. Any coordinate I can use. Now I transform all the x, y fundamental to the polar coordinate because variation is only on a surface, not 3D variation. Independent component is only on the surface. So x I can take as r cos theta. R cos theta is a radius, so radius would vary. And y I can take r sin theta. So in polar coordinate, that is a fundamental. X is r cos theta and y is r sin theta. Whereas any small area if I take, then that becomes r d theta, r, okay, one is r d theta and one is dr. Okay, this is x-axis and this is y-axis. This is xy plane. If there is a polar coordinate, means there is a circle. If there is a circle and this is a center and this is r, if this is r, this is r, then if I move like this, if I move like this d theta, if this is r0 angle, if I move d theta, then what is the arc? What is the arc? Arc is r d theta. If this d theta is 2 pi, then arc is 2 pi r, that is the circumference. So if I move theta, then this arc is r d theta. Okay, if I take a strip, 2D strip area, then one side is this arc and other side is this arc. If these two arcs they come together, then that make a dA. Okay, so r d theta and dr. If this is r, then this is I move dr. dr into r d theta is dA. Okay, so dx and dy, it becomes dA as per the approximation calculus. Okay, anyway, but it lines up into algebra, so it's all right. So dx and dy integration become r d theta dr, r dr d theta not, r d theta dr. Now here 1 by a square root of 1 minus x square minus y square would turn up into 1 by a square root of 1 minus r square. Now if it is, now what is the integration of 1 by a square root of 1 minus r square? And on top there is a r by a square root of 1 minus r square. It would not be very difficult. It is antiderivative is possible here. Or I can use term like u equal to 1 minus r square. Then du equal to minus 2r dr. Now it is easy. So r dr will come in terms of du and it is here a square root of 1 minus u. u equal to 1 minus r square. So it will become a square root of u, 1 by a square root of u du and like this. So if you integrate it, now the limit here is, earlier limit was x minus 1 to 1, y minus 1 to 1. X and y both converted to r and theta. So r is from 0 to a, that is the radius, and theta is 0 to 2 pi. Same thing, but this is very powerful concept to proceed further. So that we will see. Now, through polar coordinate, we calculated the surface area. Surface area is 1 by square root of 1 minus x square minus y square, provided radius is 1. dx dy integration minus 1 to 1, again minus 1 to 1 for x and y. Since xy is a xy plane, that's why I call it. It is not dx and dy. It is dA or dxy plane. So I have to integrate a square root of 1 minus x square minus y square dA, where in a x is minus 1 to 1 and y minus 1 to 1. If it is dA, then this xy plane I can keep changing the coordinate. If it is Cartesian, I can shift it to polar coordinate. In polar coordinate, the dA dA what we take become r d theta dr, where x is r cos theta and y is r sin theta. Now if I integrate, I get the hemisphere, hemis, I get the 0 to pi, I believe one hemisphere, that is 2 pi square. Someone has to calculate. Net it will come as 4 pi r square. So that is the surface we get through this. This is very powerful. Probably this is not the session that would end. So probably we'll proceed on it. So this is very powerful. So in next session, we will calculate the same concept with a spherical coordinate. But Cartesian coordinate is ours. So no one has proved the surface area is 4 pi a square through Cartesian coordinate. All at the end they shifted to either a spherical coordinate or polar coordinate. Okay, I have told a story of football match that a few students in a class, they are expecting English essay as football match. They mugged up completely football match essay, considering this is what would appear in the examination in India. People, English is not native language, so they mugged up everything. And now, when they went to examination, then there is a journey by plane. That is the essay came. And everyone came with yellow face, yellow river in China, yellow face. And one guy was happy. When they asked why you are happy, we could not write anything. Then they said that there was a journey by aeroplane and there was some problem in aeroplane. Aeroplane made a emergency landing, and then there was a football match going on nearby. Then he wrote the full essay on the football match. There are 22 players and 2 referee, 2 goalposts, and how match happens, and like that, full essay. So only 1 or 2 lines for the aeroplane, and then full essay. So whatever the approach you see anywhere in the book, at the end they come to a spherical coordinate or polar coordinate. But only ours in the circle, it is a Cartesian coordinate. We proved it, and through sphere also we proved through completely Cartesian coordinate. Okay, but anyway, polar coordinate is also powerful and spherical coordinate is also powerful. So through polar coordinate we saw how we can calculate it. Now through spherical coordinate we'll see how we can calculate it and what are the mistakes that we make in assumption. Like if we do integration and we take x equal to r cos theta and y equal to r sin theta, blindly we cannot take the way we want. There has to be some logic behind it. Like we took the Cartesian coordinate when we were calculating the integration and x equal to r cos theta, y equal to r sin theta, then it should follow the complete, because we were doing Cartesian coordinate specific centric. If that is the case, then it should satisfy x square plus y square plus z square equal to r square. If it has to satisfy, then we had to take another, that is sin phi. Now it is x equal to r sin phi cos theta, y is r sin phi sin theta, and z is r cos phi. Then it becomes 1. Then we replaced and then we calculated the first integration, and then next was through Cartesian one. Full Cartesian. Only we have proved that surface area of a sphere is 4 pi r square or a square only through Cartesian coordinate. After that, everyone has done the football match. Everyone at the end they turn up it to spherical or polar coordinate. Anyway, through polar coordinate we saw. Now through a spherical coordinate we'll see, and then we'll also see that how we can take assumption x equal to cos theta sin theta. Blindly we cannot take. Okay, it has to satisfy something. Then I can replace in the integration mode, so that we will see. So probably one more session we need, and then we'll bind up the surface area concept. Surface area, line area. You are awesome, you are amazing, because you need everything. See polar coordinate, spherical coordinate, Cartesian coordinate, differentiation, integration, vectorization, parametric vectorization, vector field, velocity vector, and then tangential surface, tangential, everything is there when we calculate the line or surface curvature or length. So we will proceed.